Today we're going to be discussing how to find the rate law for a crystal violet reaction. This is lab number 30. So we're first going to talk about crystal violet. Crystal violet is violet. It is represented by this molecule, which is fairly complicated. And it's going to react with sodium hydroxide. We're going to try to find the rate law for this. So the rate law is going to be rate equals K times crystal violet to a power times hydroxide to a power. We're going to be looking for this exponent in the rate law, and we are really not going to be finding this at all. In fact, we're going to completely not even consider the hydroxide. So how do we do that? What we're going to do is we're going to use a hydroxide concentration that is 1,000 times more concentrated than necessary. So if you look at your reactants, you're going to see in the materials here that the hydroxide is a 0.02 molar, whereas the crystal violet is a 0.00002 molar. I want to make sure I said enough zeros there, 4 zeros. So they react in a 1-to-1 ratio. So if you're only going to have this very small amount of crystal violet, then if you have a hydroxide that is 1,000 times more, when the crystal violet runs out, the hydroxide really didn't even change at all. So because the hydroxide concentration is constant throughout the whole experiment, the rate law, we can figure it out only for the crystal violet. Okay, and again, they react in a 1-to-1 ratio, as you could see in the equation. So what we need to be able to measure is the concentration of crystal violet over time and come up with a graph. So again, if we come up with a graph that comes out to be a straight line, then it's going to be zero order right off the bat. If it comes out to be a curve, then we know it's got to be either first or second. So we would try the ln, and if that's a straight line, that would be first order. And if we try the 1 over and its concentration is a straight line, 1 over concentration versus time is a straight line, then it's going to be a second order. Okay, so we have to take this a little deeper. How do we measure the concentration of crystal violet over time? Well, as I said, it does have a color, and as the color fades, as the reaction proceeds, the color will fade. So you'll see that that will change over time, but we really can't measure the actual concentration. So what we are going to be actually measuring is something called absorbance. Absorbance, I'm going to write ABS for absorbance. So instead of concentration, we're going to consider absorbance. So that's what we're going to be doing for all of these graphs. Instead of concentration, we're going to use what's called absorbance. So in order to understand absorbance, we're going to go to the end of this lab. I drew some illustrations here, and if you would like to pause and copy them over, you can. This is what we're going to be talking about on this page. So let's talk about the setup of the lab first. This is called a colorimeter, and what it does is it measures light transmission or absorbance. So colorimeter is this little box that you're going to be using in your lab, and inside what you put in is called a cuvette. Just cuvette. This is a cuvette, this little rectangular cylinder, basically. Okay, so what you do is you put a solution into here, right over here. You put a solution in here and you cover it up, and what it's going to do is it's going to pass light through this solution. Now the solution is going to absorb some of the light because it has a color. It's going to absorb some of the light, and then so less light is going to come out than was going in. So the light coming in is called the incident light. It passes through the sample, and what comes through is called the transmitted light. The device can translate that into what we call absorbance, because the less transmitted light, the more absorbed. So the device will measure the transmitted light, but then tell you the absorbance if you set it to do that. So the absorbance of this sample depends on 3 factors. We call them A, B, and C. Let's start with C first. C stands for concentration. The more concentrated this solution is, the more light it will absorb. So if you had this solution on your left here versus this one on the right, the one on the right absorbs more light because it's more concentrated. So these are directly related. The higher the concentration, the higher the absorbance. The next thing is the path length. The path length is how wide the cuvette is. Okay, so this cuvette is going to be 1 centimeter wide. Now, if you used a wider cuvette, which actually you cannot do with this device because it's made to only fit a 1 centimeter. But hypothetically, if you could use a wider cuvette, then it's going to absorb more light as well because there's more of the sample in between the incident light and the transmitted light. So the longer the path length, also the more the absorbance. So these are all directly related. The more the concentration, the more the absorbance. The more the path length, or the longer the path length, again, the more the absorbance. Last but not least, we're going to consider A, and A stands for the absorptivity constant. So whatever solution you're using in here has to have some kind of color. Certain colors are going to absorb more light than others. So you would probably guess that a purple color would have a higher absorbance than some kind of lighter orange type color. All right. So the color itself is going to determine what this absorptivity constant is, and not just the color, but actually the actual chemical that it is. That has to have a color, of course. So this A value is going to be specific to this, say, crystal violet has its own absorptivity constant. If you had some other purple thing, it would still have its own absorptivity constant, even if it was purple, but it was not crystal violet. So these three factors, again, are directly related to the absorptivity, absorbance. So the higher the absorptivity constant, of course, the higher the absorbance. So all these three things contribute to the absorbance. Now, we are not actually going to use these specific letters A, B, and C in this experiment. We're just going to have the overall absorbance told to us through the instrument. So in order to prepare this, what you have to do is you have to use what we call a blank. So a blank is going to have just water in it. So here's a cuvette, and this cuvette is going to have distilled water first. Okay, so DH2O. And we're going to put it into here before we start the experiment to calibrate the colorimeter. We're going to calibrate it so it does not count the absorbance of water itself. So even though water is colorless, it actually does absorb a tiny bit of light. So this is analogous to if you were going to weigh something on a scale, you put the dish, you hit tare, it subtracts the dish, and then you put your object in the dish, and the dish won't count. This is kind of the same thing. You're calibrating the water, so it does not count the absorbance of the water, so it's only going to count the absorbance of the actual crystal violet. And also, by the way, the cuvette itself is going to absorb a little bit of light. So it's going to also calibrate to not count the absorbance of the cuvette. Side note about the cuvette, it's a rectangular cylinder, okay? And on some two sides, it's going to be totally clear, which means you can see through it. And then on the other sides, it's going to look like this. It's going to have little ridges going down, so you could hold that. So when you hold the cuvette, you only hold it from the ridged side because you're going to put the clear side facing this way, okay? So the clear side has to be facing where the light goes through, and then the ridged side is going to face you when you're putting it into the colorimeter. So please be careful about that. Now, if you do have fingerprints on the cuvette, you're going to hold it. You can hold it from the ridge side. Then you take a Kim wipe, which looks like a tissue, but don't use tissues because they're too rough. They'll scratch it. You use a Kim wipe. It looks like one. And you just wipe the clear sides until they are free of any smudges or fingerprints. Okay? So that's the big picture of the lab. Now we're going to go through a couple little details, and you do have a little pre-lab to do as well. All right? So I tried to highlight the important points here. So let's talk about it real quick. You're going to take 10 milliliters of the NaOH, okay? 10 milliliters of that. And you're going to put that into a graduate cylinder measurement, okay? And then you're going to also have 10 milliliters of the 2.0 10 to minus fifth crystal violet as well. So 10 milliliters of each, all right? You're going to open up the experiment. Actually, you're just going to use you're not using a computer, you're going to use a handheld lab quest. All right, so you're going to keep those two separate from one another. You're not going to mix these yet. Then you're going to do the blank. That's the blank empty cuvette with distilled water. And you're going to calibrate your colorimeter, and you're basically going to hit auto cal. All right, now you're going to adjust what color is going to go through the colorimeter. Okay, you can adjust it by wavelength. So if you look at this graph, this tells you the crystal violet absorption by different wavelengths of light. Okay, so purple light has a wavelength around 400 nanometers. Red light is in like the 650 range, so 700 perhaps nanometers. Okay, notice crystal violet absorbs best in this region right here. So this wavelength, which is like a yellowish green color, is roughly 580 nanometers. That's the optimal wavelength that it will absorb. Okay, it will not absorb this purple, and it will not absorb blue very well, and it would not absorb red, which is really interesting because when you see something that looks purple, it's reflecting purple to you, but absorbing all the other colors. So it's absorbing all the other colors and reflecting purple to you. So this makes sense that it's absorbing greenish yellow the best, and it's not absorbing purple or blue really, or red, because red and blue make purple. So those colors are not absorbed, they are reflected to your eye. So this would be the optimal absorbance wavelength for crystal violet, around 580. And that's why you're going to set your colorimeter to that wavelength, right? So that's going to be right about here, 565. It only has certain preset ones. So 565 is going to be the closest one to the wavelength you want. So you're going to have to adjust it to turn the dial to that, okay? You're going to hit auto cal. It'll automatically calibrate with the blank, and then you're good to go, okay? So you're going to take your 10 milliliters of each of these, and you're going to mix them together. Let's do that. The purple. You're going to mix the crystal violet with the NaOH both together, and you're going to hit collect right away. Collect is like this it's not purple button, but it's like a red, I think, or whatever it is. It's like a triangle, okay? So as soon as you mix those two together, you're going to hit collect right away because it starts the timer on the computer. But you don't have to rush. You have a couple of minutes. It's not a computer. It's a LabQuest. Okay, while you're doing that, you're going to rinse the cuvette at least twice. I mean, I would do like, why not do 3 or 4 times and rinse it? Why? Because when you have a cuvette, it has the distilled water in it. Okay, so here's the cuvette. You have to use the same cuvette because, again, you already calibrated with that cuvette. So you can't just take another cuvette. It's like you can't just use a different weighing dish after you tear the balance with that one. So originally you had in here just the distilled water, okay? So you pour out the distilled water. But if you pour that out and then immediately just put in the crystal violet, you're going to dilute it because it has a little bit of water there. So you really have to pour some crystal violet, the mixture of this crystal violet and NaOH, then dump it in a waste beaker, pour some more of this mixture that you already mixed together, dump it, pour it, dump it, rinse like 3 times, I would say. And then now you fill it and leave it. And now it's going to be the exact same concentration as it is in the beaker where you mixed these 2 things together. All right. So after about 3 minutes, what you're going to do is you're going to wipe the cuvette again with the Kim wipe. You're going to put it in the colorimeter. You're going to look at the screen on your little handheld LabQuest. As soon as the absorbance stabilizes, you hit the button that says keep. You'll see this button right here. It says keep, and then immediately take the cuvette out and sit it on the counter. Because if you leave it in there for this whole experiment, which could take like 30 minutes or so, what's going to happen is this cuvette is going to start to get heated up because there's light passing through it. And if the temperature of this starts to go up, it's going to speed up the reaction. That's going to totally mess up your whole results because you have to have this happen at a constant temperature, which we're doing room temperature. So you're going to do this for about 30 minutes. Every minute, you're going to put it in, close the lid, hit keep, take it out. And so every 45 seconds, you're going to kind of do this. So you have 15 seconds to put it in, let it stabilize, hit keep, take it out. So you're pretty much getting a reading every minute. It doesn't have to be perfect every minute, but like close to every minute is going to be really, really good. So what you're going to do is you're going to get a graph, okay? It could look like this. It could be a straight line, or it could be a curve. You're not sure which one it's going to be. So if it's a curve, you're going to play with it and try ln. You're going to try 1 over, and we're going to figure out, is it 0 order, first order, or second order. So that's the big picture of the lab. And we're also going to find the rate constant. We're going to find the half-life. That'll be in the calculation. So fill out this pre-lab. This is your job right now. Based on what I just told you, you can look at this graph one more time to help you out. And this is the setup you're going to use for the time when you do the lab.